All right, let's take a look at section 12.6, which will cover cylinders and quadratic surfaces. And this section is going to be all about how to draw cylinders and quadratic surfaces. So we're mostly going to be looking at drawing shapes. But before we dive into the new stuff, which will be drawing 3D figures, we're going to start with a quick review of some two-dimensional shapes. So for parabolas, we probably remember these shapes. Y equals x squared being the standard version of a parabola, and it looks like this blue shape right here that extends in an upward direction, but it could also go down if we had y equals negative x squared. But the lesser looked at, but still equally valid version of a parabola is one that opens left or right instead of up or down. So the horizontal parabola, x equals y squared, drawn here in green. And so we'll want to remember that both of those shapes are indeed parabolas once we start looking at opening these shapes along different axes. So the important characteristics of a parabola, we have one linear and one square term. One linear term, one square term. A linear term being a variable, either x or y, that is raised to the power of 1, and a square term being one that's raised to the power of 2. So a first order term and a second order term might be another set of words we could use. We also have ellipses, the most common ellipse being a circle. And this thing has the equation x squared plus y squared equals 1. And yeah, that thing's just some sort of elliptical or circular shape. Ooh, let's actually try and draw a circle in here. There we go. We'll use some technology to our advantage here. And it kind of doesn't matter which direction we look at. A circle or an ellipse is a circle or an ellipse in either direction. So just look at one example of an ellipse. And then also hyperbolas. And so a hyperbolic shape is one that's defined by a linear asymptote. So I've already sketched in the lines y equals x and y equals negative x over to the right to sort of help guide us to create these shapes. And hyperbolic equations tend to look something like y squared equals x squared plus 1. Or if we write that another way, y squared minus x squared equals 1. And that's one where we should have the point 0, 1, should be up here. We'd also have the point 0, negative 1. And these shapes look somewhat like parabolas, except that instead of having quadratic shapes to them, their end behavior looks linear, meaning that they've got these linear asymptotes to the left and right. So as x becomes large in either the positive or the negative direction, this hyperbolic shape gets closer and closer to its asymptotes of, in this case, y equals x and y equals negative x. That being one example of a hyperbolic shape, the other being the one that opens horizontally, which would have the equation x squared equals y squared plus 1, or alternatively, x squared minus y squared equals 1. And then this one, we should see the point 1, 0 and negative 1, 0. Both fit that hyperbolic equation. And again, this thing should open up and then become hyperbolic, meaning again that it follows a linear asymptote for large values of x. So those are some 2D shapes that'll help us out as we move into the 3D shapes that we're hopefully going to be drawing. So let's start with some definitions. So we'll say that the intersection of a surface with planes parallel to the coordinate planes are called traces. So that just means if we're basically going to look at what would happen if we projected some three-dimensional shape back into the, say the XY plane or the XZ plane, YZ plane, whichever one we want to go to. We'll just call those things traces. Oftentimes they might also be called cross sections. But a cross section would just let us take a trace in any direction, whereas traces must be specifically planes parallel to a coordinate plane. And then we'll also come up with a fancy definition of a cylinder, which if we read the textbook definition, cylinder is a surface that consists of all lines, which are called rulings, that are parallel to a given line and pass through a curve. But that definition kind of sucks. So we're just we'll look at some pictures later on and then sort of revisit this definition once we can kind of look at something and decide what a cylinder is. Since cylinders that we're normally used to calling something a cylinder will still be cylinders in this sense, but also there's a mathematical cylinder that sort of extends that definition. So for example, z equals y squared plus 1 in 3 space is an example of a cylinder. We want to look at why. So for the first part, I've just graphed z equals y squared plus 1 in the yz plane, making it just a two-dimensional shape, a parabola like we're used to seeing. But now we want to extend that idea of a z equals y squared plus 1 into 3 space, meaning that there's the third variable. In this case, it's x, which isn't listed, and x can be whatever it wants. So what I'm going to do is draw a few of the rulings of this shape, which are going to be all lines parallel to the x-axis. So we'll just sketch a few of them in here. Just a few places along this shape. Using our straight edge to get those in there. It looks like that last line didn't want to cooperate. But so we might end up with a shape kind of looking like this one. Let's actually offset that last one because it was a little bit too close to the line I had going through the origin. Let's maybe bring it all the way up here. Come on. All right, so we'll look at these rulings. And I'm going to extend that shape that we just drew, the z equals y squared plus 1, further along the x-axis. So if I just copy and paste that shape in, and just let it move along the y-axis or the x-axis, I get a shape that goes here. If we do that one more time, continuing to move this shape along the x-axis, I end up getting this cylinder shape that shows up, where it's going to be the same parabolic curve in each trace, where again, these traces are going to be all planes that are parallel to the YZ plane, since that's where I started. I'm extending along the rulings to have these other traces to create a three-dimensional shape that extends all the way along the x-axis, go infinitely in either direction. So if I just kind of extend these lines, I end up with a three-dimensional shape, which hopefully you can kind of see it starting to take shape in this diagram, in this figure that we're attempting to draw. So in the case where I want to call this thing a cylinder, I'm saying it's a cylinder because all of the rulings that I just drew were straight lines that were all parallel to one another. So I'm going to skip over the definition of a quadratic surface for just a moment to come down and talk about these three figures, figures 1, 2, and 3, which all show shapes of cylinders. And let's start with figure 2 and 3, since those are sort of, if I said, think about a cylinder, you'd probably have an image looking like 2 or 3 that pops into your head. And I want to extend that definition of a cylinder into the mathematical definition of a cylinder. So when we have these cylinders, we can draw, a cylinder is comprised of two circles, maybe some distance apart, and then I can draw a series of straight parallel lines that connect those two circles together right along their surface. Those being these lines over here, 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 here. Or if I'm looking at this cylinder in the middle, I'm looking at these straight lines that connect one circle to the other circle. And that's what we want to use to define a parabola in a mathematical sense. Is that I can connect two similar shapes using a series of straight lines that are parallel to one another. So what that means is I'll take some two-dimensional shape like a circle or a parabola and then extend it along the third axis, whichever axis I wasn't using in that two-dimensional shape. And extending along straight lines in that third axis is what will give me a cylinder. So we're going to say that cylinder 1 is, or that figure 1 is also a cylinder because I can start with a parabola, in this case in the XZ plane, and then extend along straight lines parallel to the y-axis to come up with a cylindrical shape. And so that's when we say that, the rulings are all straight lines that are parallel and pass through a curve, then that's what we're talking about. So notice that we don't want these rulings to go around the curved edge because in order to have a cylinder, we cannot have curved lines, or we won't have curved rulings. So we have to be going in the straight direction. So also with the cylinders, we aren't going around the circle with our rulings. We're going from one circle to the other circle to create the rulings. So it's the same thing with the parabolic cylinder, that being figure 1, where I don't want to go around the curve. I want to go perpendicular to the curve so that I have straight lines all parallel to the axis that we're extending along. Okay, but then let's come back up to the other definition that I wanted to talk about, which is going to be the definition of a quadratic surface as opposed to a cylinder, which a cylinder could be a quadratic surface. But in general, a quadratic surface is the graph of a second degree equation. Second degree meaning that we're collecting only terms that have degree 2 or lower. So all of the squared terms, x squared, y squared, and z squared, belong in a quadratic surface equation. The mixed second degree terms, that being xy, xz, and yz, are also all part of a second degree equation. Since if I add up the degree of all the variables in each term, I'll get to 2, x times y. Each x is degree 1 and y is degree 1. Together they make degree 2. And then we'll also collect the first order terms as well, being just terms of degree 1, so just x, y, and z being those degree 1 terms or first order terms, and then also plus a constant, where I'm using letters a through j to just represent coefficients. And those are constant numbers. As it turns out, the quadratic surface equation in 3 space gets kind of complicated since we have to use letters a through j. So we're going to look at simplifying those equations to just look at a series of about 6 graphs that are the set of 6 possible quadratic surfaces. Since I can simplify that first equation through a series of rotations or translations to terms that no longer depend on a mixed set of variables, and also I can simplify it down, again through rotation and translation, so that I only have one term for each variable. So what that means is that I might, if I've got some shape, I could rotate it so that it extends along one of the axes instead of some arbitrary direction. And also we'll center this thing at the origin through translations, so that I can have a series of square terms with some constant term added in as well. Or if I've got a linear term involved, I'll only need 2 other square terms, and also I'll be able to center that at the origin without the use of a constant term. Blah. So a lot of that to say that we can simplify a lot of these quadratic surface equations. Also, when we're looking at just the simplest forms of each of these shapes, I'm going to set it up so that our constant term is either 0 or 1, just to simplify it a bit. So we won't have to deal with other negatives or other constant terms. It's if we have a constant term, we'll fix it to be 1. If we don't have a constant term, it's 0. So looking at extending some of those 2-dimensional shapes, starting with an ellipsoid. The most common type of ellipsoid being a sphere, and it'll have the equation x squared plus y squared plus z squared, each over some constant, so x squared over a squared plus y squared over b squared c squared, all equal to 1. And if we look at the traces of an ellipsoid, we should end up with just ellipses. So that if we were to look in the xy plane, we get the trace x squared plus y squared equals 1. I'm just going to ignore some of the extra coefficients for now, so I can just look at the simplest case. If I look into, this is going to be the xz plane, I get x squared plus z squared equals 1. And into the yz plane, I've got y squared plus z squared equals 1. And so by looking at the traces in each of those coordinate planes, I can come up with a rough idea of what this shape will look like. So in the simplest case, circles in each of the planes. And if I just put those together, I end up with a sphere, or in general, an ellipsoid. Characteristics of an ellipsoid include 3 square terms, and all of those terms are positive. Let's compare that then to an elliptical paraboloid. So notice that paraboloid shows up, and the parabolic shape that we are used to is y equals x squared, which consists of 1 linear term and 1 square term. So if we're going to have an elliptical paraboloid, that means we should still have some sort of parabolic shape that shows up, meaning that I'll need to have I'll have to have 1 linear term paired with some square terms. And if it's elliptical, that means that the traces of this shape in at least one direction should show up as ellipses. So I'm sort of combining an elliptical equation with a parabolic equation. So I still have x squared plus y squared, since that's indicative of an ellipse. And then I've also got a linear term, which is z over c, being added in. And note here, it's important that c is positive. Since if c were a negative value, I'd end up getting x squared plus y squared equals a negative number over on the right side. And, well, we can't have that since we'd end up getting no solution. So we're going to fix c to be a positive value here. And if we look at some of the positive and negative signs that come through this elliptical paraboloid, as long as we're still collecting all the terms on the left on one side, then I've got that both my x and both of my 2 square terms are positive, with my linear term having the opposite sign. So the linear term is negative. But we can go over to the graphs, and if we look at the yz and the xz plane, we end up with z equals y squared in the yz plane, and we have x equals z squared. Or let's try that one more time. z equals x squared in the xz plane. So the elliptical paraboloid, if I just look at parabolas in both of the coordinate planes that involve the linear term, then the traces in the coordinate plane that involve both square terms should look like ellipses. So those are those ellipses drawn in the middle. Then we'll take a look at an elliptical cone. So this one, we're going to bring up shapes that look kind of similar to the ellipsoid, where we had x squared and y squared and z squared, but this time only two of our terms will be positive, while one of the terms is negative. And also there's going to be no constant term if we're in a cone. So I'll have the x squared plus y squared minus z squared equals 0. So if I look at each of the if I look at the xy plane, or sorry, the xz plane or the yz plane, the one where those pieces are, when I'm pairing it with the opposite sign, I end up with the equation y equals plus or minus z. Let's throw that in red, plus or minus z. And in the xz plane, which is the green one, I end up with x equals plus or minus z. And again, I'm simplifying the equation quite a bit so that I'm ignoring all of the constants or all the coefficients, basically pretending that they're all 1 to make it slightly easier to sketch. But again, in that yz plane and in that xz plane, I'm just looking at a couple of lines so that it makes a sort of an X pattern. And then all of the traces that go in the xy direction or in the xy plane, I'll still have x squared plus y squared equals some constant. Where now, well, let's, instead of calling that j, we'll call it z, so that I have still some sort of elliptical shape, with the exception of right at the origin where everything comes together at just a point. And so when we talk about a cone in 3 space, a cone can extend in both directions along its axis. So a cone ends up being more of an hourglass shape than just a standard cone. So if we think of a cone as just coming to a point, in mathematical terms, that would be half a cone, I guess. So our elliptical cone, it has ellipses as its traces, and it's got the cone that extends in both directions. Okay, then hyperboloids is the next fun part. And we're going to look at 2 different types of hyperboloids, one that's of 1 sheet, one that's of 2 sheets. Just basically means whether or not our hyperboloid is connected or separated. And this is going to take the hyperbolic shape that we looked at the beginning of the lesson and extend that out into 3 space. So we know by the review that we did earlier that a hyperbolic shape is going to have linear asymptotes. So I've sketched those in. I've also put the YZ plane down already, so that we're looking at y squared equals z squared plus 1 would be those 2 blue shapes. And then we'll try and extend out into the XZ plane, where that XZ plane, we just ignore y. We should have x squared equals z squared plus 1. And again, I'm ignoring all of those coefficients, save for where I need things to show up as positive or negative. Meaning that I should still have hyperbolic shapes in this plane as well. keep this from getting too complicated, I'm not going to draw in those asymptotes. They go in the XZ plane because I think the diagram will just end up too chaotic. But then I can look at traces in the XY plane. And I see that I once again end up with ellipses if I go in either direction. So things that end up being important on the hyperboloid of one sheet, meaning that I can just construct the entire three-dimensional shape with only one continuous surface. I have, again, 3 square terms, and one of them is negative, but there is a constant term this time, compared with a cone where the constant term was 0. So if I have 3 square terms that are not all positive, but the constant term is 0, I'll end up with a conical shape. But if I have 3 square terms and they are not all positive, and there is a constant term, I will end up with a hyperbolic shape, one of the 2 types of hyperboloids. And yeah, if I only have the one, if I set it all equal to +1 and I have 1 negative term, I'll end up with 1 sheet. And if I have a hyperboloid that I set equal to +1 and I have 2 negative terms, that means I'm going to end up with a hyperboloid of 2 sheets, which is going to look like the next example, where again, I've sketched out the YZ plane. This time we've got the equation z squared equals y squared plus 1. So if we add that over, and if we look at the XZ plane, we should end up with z squared equals x squared plus 1, where I should still have some hyperbolic shapes. But this time, my 2 shapes aren't going to connect to one another. I'll have one that's above and one that's below. So if I then go to connect those shapes together, let's try and actually redraw this one. I will still have some elliptical traces, but the hyperboloid of 2 sheets won't connect back to itself. So I've got 2 sheets, meaning that I've got a hyperboloid that is separated from itself. One that extends up along an axis and one that extends down along an axis. And another easy way to check if I have a hyperboloid of 1 or 2 sheets is to see how many axes actually intersect with the surface. So if I check the hyperboloid of 1 sheet up at the top, I can extend along the x-axis, or I have an intersection along the x-axis. I can plug in the point 1, 0, 0 and have a solution. Since 1 squared plus 0 is 1, I can plug in 0, 1, 0, 0 plus 1 plus 0 or minus 0 is equal to 1. So I have an intersection along the y-axis, but I do not have an intersection along the z-axis. Plug in the point 0, 0, 1, and you get 0 plus 0 minus 1, which is not equal to 1. So I intersect with 2 axes, but not the third, so it's a hyperboloid of 1 sheet. And a hyperboloid of 2 sheets will only intersect with 1 axis. In this case, it would be the z-axis. You can check 0, 0, 1, plug that in, and we get a solution of 1, so that's good. But if I try to look at an intersection along either the x or the y-axis, I will not end up with an intersection, since in both cases I would get -1 equals 1. And finally, a hyperbolic paraboloid. So notice that paraboloid came back up again, which we know is the equation y equals x squared, or that's the most general parabolic shape. So if I've got a parabolic shape, I know I should have some mix of a linear term and a square term, so a first order term and a second order term. And I have something that looks like this equation, where now I've got x squared minus y squared plus z equals 0. Again, we'll just look at c being a positive value, just for the sake of simplifying our shapes. And I sketched in the yz plane once again, z equals y squared. But if I take a look at the xz plane, I end up with z equals negative x squared. Just solving that equation for z equals x, and again, ignoring any constant terms, which means that in the xz plane, I've got a slightly different looking shape, where in one direction, I have a parabola that opens up, but in the other direction, I have a parabola that opens down. And this shape ends up looking kind of wonky. And so I'm not going to try to sketch out all of its level curves here because I think that'll just make it look more confusing. But I think the easiest way to describe the shape of a hyperbolic paraboloid is that it looks like a saddle. And think of like a saddle that if you're riding a horse, you put a saddle on there. It's got a U that opens up in the direction where you grip the front thing of the saddle, and then it opens down in the direction where you send your legs. That's a hyperbolic paraboloid, roughly speaking. If we go to a table out of the textbook, you might find that some of these figures are easier to look at than some of my sketches. As for my sketches, I try to keep them just sort of bare bones and simply looking at planes, and then the textbook pictures can help us extend those figures into three-dimensional objects. So we look down into the lower left where we've got that hyperbolic paraboloid. You can see that saddle shape I was hopefully describing show up. So let's take a look at some similarities and differences between these shapes one last time. So for the two types of paraboloids that we looked at, we again know that this means, since it's a paraboloid, we should have a linear term, so at least one first order term and a couple of second order terms. And then we'll look at how those equations compare. For an elliptical paraboloid, we know that the traces should be ellipses. So our inside function, we have x squared plus y squared. So z equals x squared plus y squared, so that our traces looks like ellipses, as opposed to a hyperbolic paraboloid, where we want our traces to look like a hyperbolic shape instead of a parabolic shape. So in that hyperbolic paraboloid, our inside is x squared minus y squared. So z equals x squared minus y squared. Just meaning the two square terms do not have the same sign if it's a hyperbolic shape, whereas the square terms do have the same sign if it's an elliptical shape. Again, we looked at the two different types of hyperboloids, where if we set it equal to 1, a hyperboloid of one sheet will have one negative square term, whereas a hyperboloid of two sheets is going to have two negative square terms. And again, fixing it so that it's equal to positive 1. Then we'll also look at a conical shape compared to those two hyperboloids. So if we're looking at a conical shape, we know that the constant term is 0. So j equals 0 in a cone. But in hyperbolic shapes, we have that our constant term is not 0. So just anything but 0. In this case, I fixed it so that it's 1 for simplicity's sake. So j is non-zero our constant term for both types of hyperboloids. And then comparing an ellipsoid with either a cone or a hyperboloid. Ellipsoids, we had that all 3 square terms are positive, whereas in cones and hyperboloids, we have at least 1 negative square term if we collect all our square terms on one side.